Okay, everybody. So, in this video, I wanted to make a special point to make sure that once we learn the chain rule, that I put some special emphasis on when to use it. Okay. And by when I mean if you had a problem where a situation was explained to you, um, like a word problem. I was kind of hesitating to say that because I don't really like the term word problem, but an application or something like that. Something besides just somebody giving you an equation and or a function and they say, "Can you tell me the derivative of this?" All right? So, in this video I want to explain that there's a situation and all these things are happening and I want you to tell me some result. Okay? So, but let's warm up a little bit and get to that point and talk about the basics of the chain rule once again. All right, and then I'll show you the application that I have in mind. So when and how do you use the chain rule? Well, so the chain rule is used to calculate the rate of change or the derivative of a composition function or a composition of functions. So a composition of functions is something like this. All right. There's different ways you could say it, but I would like you to see that these are the same thing. Say that there's some variable t, and if you know what t is, then you can calculate this other variable u. But then if you know what u is, you can calculate this other variable y. That's a composition of functions. It's like the result of one function is fed into the other one, where there's three variables total. And the u is the one that's in the middle. So you could say, like, well, all that really happens here is that I start with t and I end up with y. And that would be accurate about it. So I could assemble these equations together, you might think, and I could put them like this, but same thing, right? You start with t and you end up with y. If you wanted to see that there was something in the middle that connected t to y, you could call that u, all right? So these are the same thing, though. That's what I mean, or that's what a composition of functions is, and that's the way I'm going to talk about it in this video. Maybe when you took algebra, you learned a composition of functions f and g is f of g of x, and that's still true. It's just that in math we have to use notation, we have to use symbols to write everything down, and although that's perfectly accurate, it's not what I have to choose one way to write it down and kind of stick to it. So that's not how I'm going to do it. All right. Now, I think that for the purpose of doing calculus and learning about the chain rule, it might be nice to think about the variables this way. Remember how I said, well, what happens here is that there's some variable t, and once that's given, you can figure out this other one u, and once that's figured out, you can get this ultimate answer y. Well, so it's like there's this chain. Maybe that's why it's called the chain rule. There's this chain of cause and effect where, say I told you that t was 2. Well, then you could calculate that u is supposed to be 8. And then once you know that u is supposed to be 8, you calculate y to be 136 by those equations. Okay? So there's an order of operations. You're given t, you calculate u, and then you calculate y. There's a chain for over which the variables are linked together. Now, I can't. You can understand calculus however you want, and not everybody thinks about it the same way I do. But I might at least encourage you to try to think of things like that. It seems to make sense to me to think of it like that, so that's the way I'm inclined to tell you about it. Okay. Now, all right, so say that we can accept that much about this. Let's take it a little bit further. So if ultimately I plug in t and I get y, that's kind of like saying, well, t is the input variable or the independent variable, and y is the output variable or the dependent variable. And since calculus deals with changes, well, so real quick. So algebra deals with one number giving you another. You plug in 2 and you get 136. We don't really talk about changes or the influence of change in algebra, but in calculus, that's what we do. So not only is it true that if I know t, I can figure out what y is, it's also true that any change to t has this ripple effect down the change and causes some change in y. I hope that's easy to believe, like no matter what the situation is, that change in t is probably going to cause some change in y. But in calculus, we want to know how. Does y change a lot? Is it really sensitive to change in t? How sensitive is it to changes in t? That sort of thing. Another way to phrase that question is, what's the rate of change of y with respect to t? Or what's the derivative? Or what's dy over dt? All right, so that's what really I'm interested in when I'm doing calculus, and specifically this time when we're talking about the chain rule, okay? All right, so in this situation, when we have a composition function like this, t determines u and then u determines y, then there's the derivative, okay? We can find the rate of change of y, this variable, with respect to t, this one, that's this, by finding the rate of change of u with respect to t, that's this, and multiplying it by the rate of change of y with respect to u, that's this, okay? So there's our derivative of y with respect to t. Okay, now this is one of a few different ways that you could write the chain rule down, and it's not the only way that you'll see it. And of course, the variables could be different. They could be a, b, c, x, y, z, and it really doesn't matter what the variables are. It's the structure of this that I'm trying to get you to understand, okay? All right, so that's how I'm going to use the chain rule in this video, even though there's other ways I could write it down. So let's look at an example, and I would like you to see if you understand that the chain rule is applicable to this. Okay, so here's the scenario, and this is contrived, but I want something for my lesson here. So even if you think it's kind of silly, it does get the point across. Suppose that I'm here and there's this once in a lifetime occurrence of me seeing a UFO, okay? All right, and what I notice, let's say, is that the UFO is rising vertically, meaning perpendicular to the ground, at a constant speed of 4 meters per second. So I just happen to notice that, let's say. So it's rising vertically in a straight line at a constant speed of 4 meters per second. When I say constant, it means it's not speeding up and it's not slowing down. It's moving 4 meters for every 1 second that goes by, okay? I'm standing 100 meters away. So, okay, let's let that sink in. All right, it's a pretty extravagant thing to see a UFO. Suppose that, given that, I want you to calculate how fast the UFO is moving away from me when it's 10 meters above the ground. So it's like, I want to know, sure, it's moving up, but it's also moving away. Like, so this distance r from me directly to the UFO, that's changing also. Because if it's going this way, the height of the triangle is getting bigger, but so is the hypotenuse, so is this distance. So, it would make sense that, yeah, if I know how fast it's rising, I could tell you how fast it's moving away, okay? Now, what about this makes it chain rule, okay? What about the situation makes it such that it belongs in this video and I can use the chain rule? Well, let's think of it like this. How are all the variables linked together? I mean, what variables do we have? Well, time is one of the aspects of this problem because it's moving, and so there's a clock running, so time is part of it. There's also y, which we could say is the altitude, okay? And then there's also r, which we could say is the distance from me to the object, all right? So there's 3 variables, there's 3 things: time, altitude, and I'll just say distance. So I think that's what makes it chain rule. But let me put a finer point on it than that, okay? There's those 3 variables I was just talking about, but they're in composition because if I know time, then I could figure out the altitude. Now, I actually don't know the function that would do that. Like, I can't say that at time t is equal to 2 seconds, then the object is 20 meters above the ground. I can't do that, all right, because not enough information is given. But it is possible that because it's moving, that time determines its altitude. Yes. Like, is it true that at every time it has to be some number y meters above the ground? Okay, yes, that's true. Even if I don't have an exact equation. It turns out I don't need one, though. Okay? But okay, yes, there's that link. And then if I know the altitude, could I calculate r, the distance from me? Well, so think about it. You took pre-calculus or you took trigonometry to get into this class. If I know, like, okay, there's me, there's the UFO, and between me and that and the ground, there's a right triangle. If I knew this and I knew this, could I figure out that? Yeah, you use the Pythagorean to do that. So yeah, there's a function where y gives you r. So at every time there's an altitude, and at every altitude there's a distance. So there's a chain, there's a composition of functions. So the chain rule is the right thing to use. So what was the chain rule going to tell us? Well, the rate of change between this variable and that one, dr dt. Oh, that's how r is changing with respect to time. That's how it's moving away from me, is equal to the rate of change of y with respect to t. Well, that was given. When it was said in the problem that the UFO is moving vertically at 4 meters per second, that's dy over dt. That's how its altitude y is changing in time. Okay? And they said that, or it was said that the rate was constant, so that is the derivative. And then times the change of y with r with respect to y, dr over dy. Okay? Now, that derivative I can find from the function where r is a function of y. But there's the chain. That's how the variables are linked together in this problem. And then here's what the chain rule says is the derivative of r with respect to t. And that's what I'm after. That is, in calculus notation, how fast the UFO is moving away from me, given that r is the distance from me to it. All right? Okay, so I've got the chain rule written down. Now I'll calculate everything. Now, I said that dy over dt, that was given to be 4 meters per second. About this one, okay, I get, it's whenever I first went over, when was that? When I covered Leibniz notation, I said, well, this is Leibniz notation for the derivative. And to find dr over dy, you need r, the variable on top, to be a function of y, the one on the bottom. So if we look at that triangle, we can get this function. Okay, well, how's that? Well, because one, it is a triangle. It's a right triangle. So this side squared plus this one squared equals this one squared. So we get 100 squared plus y squared equals r squared. And if you need r to be a function of y, you can solve this fairly easily for r, and you get r as a function of y as root 100 squared plus y squared. Then we find the derivative of this. What also happens to be with the chain rule applied to just the function. And that's half 100 squared plus y squared to the power negative half times 2y. With a little simplification, we'll get this. Okay? All right, so there's dr over dy. That's this. So we get 4 times dr over dy, which is that. Okay? Okay, now there's our dr over dt. That is the rate of change of the distance r with respect to time. And what were we going to do? Question was, how fast is the UFO moving away from me when its altitude, or y, is 10? Okay, so I've got dr dt. I want to evaluate dr dt when y is 10. I'll get this. And it turns out it's about 0.398 meters per second. Okay? So it's not moving away from me very fast. that doesn't seem too far off. I mean, think about it. If this is rising at a constant rate, when it's relatively low to the ground, it's not going to seem like it's moving away from me very quickly. But the higher it gets, you're looking more up at it. You're seeing more of its vertical movement. So if I had done this question with a much greater altitude, it would have seemed to be moving away from me more like 4 meters per second. But as it is, when it's fairly low to the ground, when y is 10, that's how fast it's moving away from me. So I'm watching it. It's moving vertically through the air at 4 meters per second, but I'm seeing it go away from me at 0.398 meters per second. Okay? All right, so first example is done. So from there, I wanted to mention a follow-up question just because I thought I could get a little bit more mileage out of that question we just did, to emphasize a few other things. So suppose we just did that question. All right, okay. Do you know the difference between dr dt and dr over dy? Dr dt and dr dy. And I just mentioned that. I remember I had a student one time who was an electrical engineering major, and he took all calculus classes from me and then transferred and started taking physics courses and electrical engineering courses. And he said, I don't know what to do. I just see derivatives everywhere in everything I do, and I don't know how to make sense of it. And I wanted to say, well, when we covered this kind of thing, I gave you a way to at least understand what the derivatives meant. Now, maybe the bigger picture with whatever else you're doing and the complexity of the math there, that's another story. But at least, like, when you see any individual derivative, you can understand what it's trying to measure, okay? So think about that. What's the difference between these? Well, dr over dt, r on top, t on the bottom, that's the instantaneous rate of change between the distance r and time. It's how far the UFO is moving away from me. It's how fast the distance r is growing, okay? So at least if I see that, I can verbalize what it means, okay? What about this other one, dr over dy? Okay, so r on the top, y on the bottom. It's a derivative. It's an instantaneous rate of change. This is the rate of change of the distance r with respect to the distance y. Well, so that's different. This one doesn't involve time at all, really. I mean, it has nothing to do with time. It just says, we've got a triangle. It's a right triangle. Say that's 100 meters. That if this distance changes, well, then so does that one. Okay, no surprise there. It tells me how. So it might be that for every meter taller this triangle gets, that r gets so many meters bigger too. But I mean, we can agree that change here is going to cause change here, and this is the rate of change between them. Okay? So that's the difference. That's the difference between them. You can look at your variables. They're both rates of change. Both of these tell you how two variables are changing together, one with respect to the other. But one of them involves time and motion, and the other really doesn't. Okay? All right, so let's see then if you could do this. Could you, with respect to that situation that was in the last problem with the UFO going vertically upwards from me, where I stand 100 meters away, the UFO travels vertically at a constant speed of 4 meters per second, that situation, can you find dr dt when y is 10 and dr over dy when y is 10? Well, dr over dt, that was the whole purpose of that last question. And this is what we got. But what about dr over dy? Well, finding that was part of doing the question. But I want to make sure that you could find this on its own, okay? That you realized what part of that question this was. So dr over dy. You get that from the function where r is a function of y, okay? All right, and that's this right here. R equals root 100 squared plus y squared. And we use the rules for finding derivatives, and we get like that. Now, the rules, those were covered in another video. So there it is. There's dr over dy. So then you want y to be 10. Okay, so you put 10 and 10, you'll get this, and you'll get that. Okay, so between the two of these, this means that when the UFO is 10 meters above the ground, for every second that goes by, it can move about 0.398 meters upwards, right? Because that's where it's moving. That's the instantaneous rate of change when it's 10 meters above the ground. If it was 100 meters above the ground, that would be a different number. But when it's 10, that's how it appears to be moving to me. This says what, though? Remember, that's dr over dy. It's the change in r over the change in y. This number is roughly equal to what? Delta r over delta y. The change in y, the change in r. So we could say that this number is roughly means this. If y were to increase by 1 meter, we would find that r wouldn't increase very much at all. Okay? When y is 10. So sure, what we're seeing is that when this side of that triangle is significantly shorter than this side, any growth in this side here doesn't seem to affect that one very much. Okay? That's when y is 10. When this side is relatively short compared to that one. Any growth here does not cause much there. So like the proportion would be 1 meter in growth on y from 10 would cause 0.09 or so meters of growth in r, which that's a lot less than 1, isn't it? Okay. All right. So, okay, I did the problem, and then I tried to review a little bit about the notation. Let's do another one. All right. So here I have the same theme as the last question, where I want to present you with a question, I want to present you with a scenario, and then I want to see if you understand that the chain rule is appropriate. Okay. So suppose we have this cylindrical container, and it happens to have a radius of 7 centimeters. Okay. And let's imagine that liquid is poured into it at a rate of 0.2 gallons per minute. Okay. So 0.2 gallons per minute. Now, so think about that. However you want to measure it. If you were pouring liquid into this, you could say liters per second or gallons per minute. It's going to be volume over time. This is just a description of how that's happening. Okay, so that's a description of something going on. Now, I hope that this situation, like the last one, even though the last one did involve a UFO, which maybe not everybody believes in, they were at least situations where you could understand them before we even did the math. Like, you know what it is to watch something and see it moving away from you. Or if you have a container, you know what it would be like if you could put this under the faucet or something like that, and then turn the faucet on so that liquid or water's coming out of it at a constant rate, okay? All right, so there's my setup for you, and I want to ask you, how fast is the fluid level rising? I mean, if the liquid's getting poured in, this depth h is going up, however so quickly it's happening, all right? Okay, so let that sink in. See if you can think of how the chain rule is applicable to it. Here's how I would think of it. So if we were to fill up this container as described, then there's time, right? Because I told you, well, we're pouring liquid in 0.2 gallons per minute. So time is an aspect of this problem. I've told you how fast something's happening. So time determines how much volume is in the container. Isn't that true? Isn't there a different amount in here at time t is equal to 1 minute than at time t is equal to 2 minutes? Yeah, there's 0.2 gallons more at 2 minutes than 1 minute. So the time definitely determines the volume of liquid in the container. But the volume of liquid in the container determines how deep it is. If I said this is so many cups or gallons or liters of liquid, then that would determine, well, it's in this container, it's got to be like so deep, okay? So sure, yes, the time determines the volume because I know how fast it's being poured in, but then the volume or the amount in the container determines how deep it is, okay? So T determines V determines 8. There's your chain. I have this order of operations. I have a composition of functions. So I could do this. I could tell you with the chain rule, the rate of change of H with respect to T, dH over dt. What would you call that? That's how fast the liquid is rising. The change in the depth over the change in time. Okay, definitely, yeah, that's it. That's how fast the liquid is rising. That's equal to the change in volume with respect to time. That was given. That was 0.2 gallons per minute. Okay? So that was given times the change in the depth with respect to the volume. Okay? How the volume changing causes the depth. That's what that derivative is. Isn't it true that if the volume got bigger or smaller in the container, the depth would also have to get bigger or smaller? Yes. Okay. So we want this one. This one was given, and that one we can figure out. Okay? So how are we going to find dH over dV? So how does that work? We need the volume to be a function, the depth to be a function of the volume. Okay, so for this derivative here, I need H to be a function of V. And considering that liquid would take the shape of the container, if I'm pouring liquid into a cylindrical container, this is a cylinder, then yes, the volume does somehow determine the depth, all right? Volume of a cylinder, a right cylinder, is pi times the radius squared times the height or depth, whatever you want to call it. So to find this derivative, dH over dV, I need H, the depth or the height, whatever you want to call it, to be a function of the volume. So let's see, it's volume equals 49 pi h. Volume equals r squared. Now the radius was given to be 7, right? Okay. R squared pi h. And I need what? The depth h to be a function of the volume v. So I could do a little arithmetic right there and say h is v over, I'll divide by 49 pi. So h is v to the first power over 49 pi. So I could find dH over dV as the derivative of this. What would that be? 1 over 49 pi. All right, so here it is. dH over dt is, here's dV over dt. Why didn't I just write 0.2? Well, we have a little bit of a mismatch in units here. What are the units of dV over dt? Volume over time. It was given to be 0.2 gallons per minute. But notice how the units are going to be needing to cancel. So this, how the depth is increasing in time, that's going to be centimeters per minute. Okay? So I've got to convert gallons per minute to cubic centimeters per minute. I have to make all my units agree with each other. So if I'm measuring distances in centimeters, then that volume right there is going to have to be in cubic centimeters, not gallons. All right. So 1 gallon is, it turns out, equal to 3,785.4 cubic centimeters. So if I take 0.2 times that, that is dV over dt with units converted to cubic centimeters per minute. This, dH over dV, gotten that way, 1 over 49 pi. Multiply it all together, that's dH over dt, that's 4.92 centimeters per minute. So you can pour the liquid in at 1/5 of a gallon per minute, but you'll see it rising as it's poured in that container, almost 5 centimeters per minute. Okay? All right. So Look at the units here. This would always happen in the chain rule. Sometimes when the chain rule is explained, and I may have even said this, I probably did say this in another video that I made, is that look how the units cancel. You want to find dH over dt? Well, this thing you set up over here should cancel that way. Okay, so dv, cancel. Okay, you get h over t. So, all right, dH over t equals, if the canceling is applied, I get dH over dt there too. So check. They agree with each other. Okay, even though we don't really cancel that, it does have that appearance, and if you want to think of it that way, it's okay. All right, so same here with the units, right? Cubic centimeters per minute and centimeters per cubic centimeter. Cancel, cancel. Okay, I'm going to get a number that makes sense. What kind of units make sense for how the depth is increasing? Centimeters or inches or feet, distance over time. Now, since we were measuring distances from the beginning in centimeters, it makes sense that dH over dt would be in centimeters per minute. Sure enough, once I converted, I'm getting cancellation to be centimeters per minute. Okay. All right, so we did it. I maybe put special emphasis on how you think about the units and so on. But let me tell you one more thing to close the video with. Another way to think of the chain rule. This is sort of an intuitive way to think about it. Because you can do math by just going through the motions, and that has value. And part of what we learn is that you just learn how to follow rules in a very rigid way to certain kinds of problems. But everybody has a way that they think about stuff. And I want to encourage you to think about the chain rule like this. Take the example we just did. Here's the formula I used to find how fast the water level was rising from knowing how fast I was pouring it in. So you could think of this part of the equation, the right-hand side, as saying as time passes, the volume's going to change. That's this derivative. This derivative tells you how. As time passes, the volume changes because it's being poured in. This derivative tells you how if the volume changes, then the depth must also change, right? dH over dV. Change in depth over change in volume. So I can look at the right-hand side of the equation like that. Now you can almost see the canceling that I was just talking about right there. As time changes, or as time passes, the volume changes, right? But if the volume changes, then the depth changes. So, well, that sounds like if the depth changes with respect to time, okay? Because we started with time. Therefore, as time passes, the depth changes. So sure, yeah, time passes, volume changes, but if volume changes, the depth changes. So ultimately, if time passes, the depth changes. Okay, and that was the result that ultimately we interpreted out of the chain rule. Maybe if I just express it in words like that, you can see why that is.